Hello guys, welcome to another episode about the transformer. In this episode, we will be building the transformer from scratch using PyTorch, so coding it from zero. We will building the model, and we will also build the code for training it, for inferencing, and for visualizing the attention scores. Stick with me because it's going to be a long video, but I assure you that by the end of the video you will have a deep knowledge of the transformer model, not only from a conceptual point of view but also from a practical point of view. We will be building a translation model, which means that our model will be able to translate from one language to another. I chose a dataset that is called Opus Books, and it's sentences taken from famous books. I chose the English to Italian because I'm Italian, so I can understand and I can tell that if the translation is good or not. But I will show you which point you can change the language so you can test the same model with the language of your choice. Let's get started. Let's open the IDE of our choice. In my case, I really love Visual Studio Code, and let's create our first file, which is the model of the transformer. Okay. Let's go have a look at the transformer model first, so we know which one part we are going to build first, and then we will build each part one by one. The first part that we will be building is the input embeddings. As you can see, the input embeddings take the input and convert into an embedding. What is the input embedding? As you remember from my previous video, the input embeddings allows to convert the original sentence into a vector of 512 dimensions. For example, in this sentence, your cat is a lovely cat. First, we convert the sentence into a list of input IDs, that is, numbers that correspond to the position of each word inside the vocabulary. And then each of these numbers corresponds to an embedding, which is a vector of size 512. So let's build this layer first. The first thing we need to do is to import Torch. And then we need to create our class. This is the constructor. We will need to tell him what is the dimension of the model, so the dimension of the vector. In the paper, this is called D model. And we also need to tell him what is the vocabulary size. So how many words there are in the vocabulary. We save these two values, and now we can create the actual embedding. Okay, actually PyTorch already provides with a layer that does exactly what we want to do. That is, given a number, it will provide you with the same vector every time. And this is exactly what an embedding does. It's just a mapping between numbers and a vector of size 512. 512 here in this our case is the D model. So this is done by the embedding layer, nn.embedding, and vocab size and D model. Let me check why my autocomplete is not working. Okay, so now let's implement the forward method. What we do in the embedding is that we just use the embedding layer provided by PyTorch to do this mapping. So return self.embedding of x. Now actually there is a little detail that is written on the paper. That is, let's have a look at the paper actually. Let's go here, and if we check the embedding and softmax, we will see that in this sentence, in the embedding layer, we multiply the weights of the embedding by square root of D model. So what the authors do, they take the embedding given by this embedding layer, which I remind you is just a dictionary kind of layer that just maps numbers to the same vector every time, and this vector is learned by the model. So we just multiply this by math.sqrt of the model. You also need to import math. Okay. Now the input embeddings are ready. Let's go to the next module. The next module we are going to build is the positional encoding. Let's have also a look at what are the positional encoding very fast. So we saw before that our original sentence gets mapped to a list of vectors by the embedding, the embeddings layer. And this is our embeddings. Now we want to convey to the model the information about the position of each word inside the sentence, and this is done by adding another vector of the same size as the embedding, so of size 512, that includes some special values given by a formula that I will show later, that tells the model that this particular word occupies this position in the sentence. So we will create these vectors called the position embedding, and we will add them to the embedding. Okay, let's go do it. Okay, let's define the class positional encoding. And we define the constructor. Okay, what we need to give to the constructor is for sure the D model, because this is the size of the vector that the positional encoding should be. And the sequence length, this is the maximum length of the sentence, and because we need to create one vector for each position. And we also need to give the dropout. Dropout is to make the model less overfit. Okay, let's actually build the positional encoding. Okay, first of all, the positional encoding is we will build a matrix of shape sequence length to D model. Why sequence length to D model? Because we need vectors of D model size, so 512, but we need sequence length number of them, because the maximum length of the sentence is sequence length. So let's do it. Okay, before we create the matrix and we know how to create the matrix, let's have a look at the formula used to create the positional encoding. So let's go have a look at the formula used to create the positional encoding. This is my previous the slides from my previous video, and let's have a look at how to build the vectors. So as you remember, we have a sentence. Let's say in this case we have 3 words. We use these 2 formulas taken from the paper. We create a vector of size 512 and one for each possible position, so up to sequence length. And in the even positions we apply the first formula, in the odd positions of the vector we apply the second formula. In this case I will actually simplify the calculation, because I saw online it has been simplified also. So we will do a slightly modified calculation using log space. This is for numerical stability. So when you apply the exponential and then the log of something inside the exponential, the result is the same number, but it's more numerically stable. So first we create a vector called the position that will represent the position of the word inside the sentence. And this vector can go from 0 to sequence length -1. So actually we are creating a tensor of shape sequence len to 1. This is wrong. Okay, now we create the denominator of the formula. And these are the 2 terms we see inside the formula. Let's go back to the slide. So the first tensor that we built that's called position, it's this pos here, and the second tensor that we built is the denominator here, but we calculated it in log space for numerical stability. The value actually will be slightly different, but the result will be the same. The model will learn this positional encoding. Don't worry if you don't fully understand this part. It's just very special, let's say, functions that convey this positional information to the model. And if you watch my previous video, you will also understand why. Now we apply this to numerator and denominator to the sine and the cosine. As you remember, the sine is only used for the even positions and the cosine only for the odd positions. So we will apply it twice. Let's do it. So apply. So every position will have the sine, but only, so every word will have the sine, but only the even dimensions. So starting from 0 up to the end and going forward by 2 means every from 0, then the number 2, then the number 4, etc., etc. Position multiplied by div term. Then we do the same for the cosine. In this case, we start from 1 and go forward by 2. It means 1, 3, 5, etc. And then we need to add the batch dimension to this tensor so that we can apply it to the whole sentences, so to all the batch of sentence, because now the shape is sequence length 2D model, but we will have a batch of sentences. So what we do is we add a new dimension to this PE, and this is done using unsqueeze and in the first position, so it will become a tensor of shape 1 to sequence length to D model. And finally, we can register this tensor in the buffer of this module. So what is the buffer of the module? Let's first do it. Register buffer. So basically, when you have a tensor that you want to keep inside the module, not as a parameter, learned parameter, but you want it to be saved when you save the file of the model, you should register it as a buffer. This way the tensor will be saved in the file along with the state of the module. Then we do the forward method. So as you remember from before, we need to add this positional encoding to every word inside the sentence. So let's do it. So we just do x is equal to x plus the positional encoding for this particular sentence. And we also tell the model that we don't want to learn this positional encoding because they are fixed. They will always be the same. They are not learned along the training process. So we just do it requires cred false. This will make this particular tensor not learned. And then we apply the dropout. And that's it. This is the positional encoding. Let's have a look at the next module. Okay, we will build the encoder part of the transformer, which is this left side here. And we still have the multi-head attention to build the add and norm and the feed forward. And actually there is another layer which connects this skip connection to all these sublayers. So let's start with the easiest one. Let's start with layer normalization, which is this add and norm. As you remember from my previous video, let's have a look at the layer normalization, a little briefing. So layer normalization basically means that if you have a batch of n items, in this case only 3, each item will have some features. Let's say that these are actually sentences and each sentence is made up of many words with its numbers. So this is our 3 items. And layer normalization means that for each item in this batch, we calculate a mean and a variance independently from the other items of the batch. And then we calculate the new values for each of them using their own mean and their own variance. In the layer normalization, usually we also introduce some parameters called the gamma and the beta. Some people call it alpha and beta, some people call it alpha and bias. Okay, it doesn't matter. One is multiplicative, so it's multiplied by each of these x, and one is additive, so it's added to each one of these x. Why? because we want the model to have the possibility to amplify these values when he needs this value to be amplified. So the model will learn to multiply this gamma by these values in such a way to amplify the values that it wants to be amplified. Okay, let's go to build the code for this layer. Let's define the layer normalization class. And the constructor as usual. In this case, we don't need any parameter except for one that I will show you now, which is epsilon. And usually EPS stands for epsilon, which is a very small number that you need to give to the model, and I will also show you why we need this number. In this case, we use 10 to the power of -6. Let's save it. Okay, this epsilon is needed because if we look at the slide, we have this epsilon here in the denominator of this formula here. So x with cap is equal to xj minus mu divided by the square root of sigma square plus epsilon. Why we need this epsilon? Because imagine this denominator, if sigma happens to be 0 or very close to 0, this x nu will become very big, which is undesirable, as we know that the CPU or the GPU can only represent numbers up to a certain precision and scale. So we don't want very big numbers or very small numbers. So usually for numerical stability, we use this epsilon also to avoid division by 0. Let's go forward. So now let's introduce the two parameters that we will use for the layer normalization. One is called alpha, which will be multiplied, and one is bias, which will be added. Usually the additive is called bias, it's always added, and the alpha is the one that is multiplied. In this case, we will use nn.parameter. This makes the parameter learnable. And we define also the bias. This, I want to remind you, is multiplied, and this is added. Let's define the forward. Okay, as you remember, we need to calculate the mean and the standard deviation, or the variance for both of these. We will calculate the standard deviation. Of the last dimension, so everything after the batch, and we keep the dimension. So this parameter keep dimension means that usually the mean cancels the dimension to which it is applied, but we want to keep it. And then we just apply the formula that we saw on the slide. So alpha multiplied by what? X minus its mean divided by the standard deviation plus self.eps, everything added to bias. And this is our layer normalization. Okay, let's go have a look at the next layer.